generative AI in medicine is it's a phrase that's generating a lot of buzz, right? And maybe even some skepticism.
Hmm.
You might be thinking, is this the next big leap or, just another overhyped trend in tech? Especially for those of you in healthcare without a computer science background, it can be tough to sort through all the noise.
Definitely.
So for you, this deep dive is really about getting a clear, evidence-based understanding. What does generative AI really bring to the table in medicine? We want to cut through the jargon, the hype.
Yeah, our goal today is pretty straightforward.
Yeah.
Just to give you that solid foundation, we'll explore what generative AI can actually do, the exciting ways it's being used, and just as importantly, its real-world limitations, in a medical context.
Okay.
We're drawing from a very current peer-reviewed article, a current review of generative AI in medicine core concepts, applications, and current limitations. So think of this as like your shortcut to understanding what's truly significant for your work.
And it's really striking how different the timeline is compared to what we're used to in medicine.
Oh, completely.
Years of clinical trials, careful peer review, that's the rhythm we know.
Yeah.
But AI, things move at, well, warp speed. Fail early and often. That's a common mantra in tech, which is just a world away from the cautious, patient safety first approach we need in healthcare. It's genuinely astonishing how quickly AI capabilities are advancing.
It really is.
What was state of the art even just a year ago might be considered, old hat today. This rapid shift means you, as a healthcare professional, need to develop new strategies for staying informed, maybe focusing more on reputable synthesis reports, real-world implementation studies, not just individual research papers.
That rapid evolution really highlights the need for a different way to approach understanding AI in medicine.
Yeah.
Our traditional evaluation methods, they just can't keep up.
Right.
So in this deep dive, we'll start with the basics. What is generative AI? How is it different from other AI you might already be aware of? We'll look at the core building blocks, things like neural networks, key architectural patterns. Then we'll explore how generative AI is being applied to different types of medical data images, text, audio, even video.
Exactly.
Yeah.
And we'll also dig into some of the more specialized applications popping up, like using AI to help with diagnosis, something called Retrieval-Augmented Generation, RPG. We'll get into that. And these intriguing multi-agent systems. And because a balanced view is so crucial, we'll spend significant time on the current limitations. We're talking about what these models don't know, those tricky hallucinations we hear about, the challenge of interpretability, bias, and of course, the evolving regulatory picture.
Absolutely critical.
Okay, so let's unpack this. What exactly is generative AI, and how does it differ from the AI we might already encounter in healthcare?
Right. So at its core, artificial intelligence, AI, it involves creating algorithms that can mimic human intelligence. Things like, recognizing images, processing language, making decisions.
Okay, the broad umbrella.
Exactly. Now, within AI, we have a subset called machine learning, or ML. Here, algorithms learn from patterns in data to make predictions or decisions without explicit programming for every single task.
So they learn from experience, kind of.
Precisely. Think of an ML model analyzing a huge database of patient records to spot subtle patterns that might suggest, say, an increased risk for a particular condition.
Got it. Learning from data. And then there's deep learning, DL. How does that fit in?
Good question. Deep learning is a more specialized subset of ML. It uses these things called neural networks with many layers of interconnected nodes, often called neurons.
Okay.
These deep networks are particularly good at tackling very complex tasks, like interpreting intricate MRI scans or analyzing massive amounts of genomic data.
Right. And just to clarify the term, when we say model in this context, we're generally talking about these layered neural networks doing the machine learning task.
Okay. AI, then ML learning from data, and DL using these doc networks for complex stuff. So where do discriminative and generative AI fit into this classification? Great question. So in ML and DL, models generally fall into two main camps, discriminative or generative. Discriminative models are designed to, well, discriminate. They classify or predict based on the input data.
Okay.
Their job is to distinguish between different categories or predict a specific outcome. For example, in diagnostic imaging, a classifier model might look at a chest X-ray and decide, is there pneumonia or not? Yes, no, normal, abnormal, that sort of thing.
That makes sense, like sorting things into boxes.
Exactly. And there are other types too. Regressors, for instance, predict continuous values, like estimating how long a patient might stay in the hospital based on their initial lab results.
Ah, okay.
Segmentation models classify individual pixels in an image, maybe outlining a tumor precisely on a CT scan.
Right, finding the edges.
Yep. And object detection models go a step further. They identify what an object is, say, a specific type of lesion, and pinpoint its exact location in the image. Super useful for guiding surgery, for example.
Okay.
The key thing about discriminative models is they work with existing data to identify patterns that are already there.
All right, so they're analyzing what exists. That must mean generative AI is doing something fundamentally different, creating something new.
You got it. Generative AI models go beyond just classifying or predicting. They actually generate new synthetic data, data that looks like real-world data, but is actually novel compared to what they were trained on.
Okay, novel data.
Yeah, that's how they can produce human-like text,
Yeah.
create really realistic images, even synthesize artificial audio. Think about large language models, LLMs, like the GPPs everyone talks about.
Right.
They can generate coherent text for things like drafting parts of clinical notes or answering common medical questions. It can be a huge help with administrative tasks.
I can see that.
Then you have diffusion models. These are newer, very powerful generative models, especially good at creating complex, highly realistic images and videos. They can even generate synthetic examples of rare conditions, which is incredibly valuable for medical training, giving people exposure they might not otherwise get.
Wow, okay. So, the big takeaway. Discriminative AI sorts and understands existing info, while generative AI actually creates new content. That could
Wow.
really expand our data resources and open up new possibilities in clinics and research.
Exactly. That's the core difference.
Okay, so we know what generative AI does. Now, what are the fundamental building blocks? How does it actually work? Let's start with neural networks. What exactly is a neural network in simple terms?
Okay, well, at its heart, you can think of a neural network as a very complex, layered mathematical equation. It's designed to process data and learn the patterns within it.
An equation, but how is it different from, say, algebra?
Right. It's different because in traditional equations, we usually know the constants, the coefficients, and we solve for the unknowns. With neural networks, it's almost flipped. We start with the known data, like pixels in an image or words in a history.
No.
Those are the input variables.
Okay.
And the network's main job is to learn the best coefficients and operations within its layers by looking at tons and tons of examples of what we want it to learn.
So it's like the network figures out the recipe for diagnosing something by looking at thousands of patient cases and their outcomes.
That's a great analogy, yeah. This learning process is called training. During training, the network constantly adjusts its internal parameters, those coefficients, even its connections, trying to accurately map the inputs to the outputs in the training data. It makes adjustments, gets feedback on how well it did, and the goal is to minimize the difference between its predictions and the actual outcomes. It repeats this over and over. That's why it needs so many examples to learn effectively. It's tweaking its internal ingredients until it gets the taste the right output consistently right for lots of dishes. The training data.
Okay, so it trains on massive data, tweaking itself until it gets good at the task. What happens after it's trained?
Once trained, it essentially functions as a very complex but fixed equation.
Yeah.
You feed it new, unseen data. Those are the input variables. Now it processes them through its learned layers of parameters and operations, and then gives you a meaningful output. So for example, a network trained to spot malignant skin lesions might take the pixel values of a new skin image as input, run them through its layers, and output a probability score. How likely is this lesion cancerous?
Interesting. So it goes from learning the rules to applying them in new situations. What makes neural networks so powerful in AI today? What are their key characteristics?
Well, a really important one is their inherent nonlinearity.
Yeah.
This comes from how the neurons are interconnected in layers. Each neuron does a relatively simple calculation, but when you layer them up and each layer applies both a linear transformation and a nonlinear function,
Okay.
the network becomes capable of learning extremely complex relationships in data, relationships that simpler linear models just can't capture.
Right, they handle complexity better.
Exactly. But that complexity means they need that substantial amount of data we mentioned to optimize all those internal parameters effectively. And the training itself is very computationally intensive. It often needs specialized hardware like GPUs, graphics processing units, to handle the sheer number of calculations. It's really the combination of having huge data sets available now, the big advances in GPU power, and breakthroughs in deep learning algorithms over the last decade or so that's made neural networks so dominant in AI.
So complex, data hungry, need powerful computers. Makes sense.
Yeah.
Now, how do these networks actually represent the data they're working with? How does it go from a complex MRI scan or a long patient note to something the network can, understand and process?
That's a really crucial point. For a network to do anything useful, it has to distinguish the important information, the signal, from the irrelevant stuff, the noise.
Okay.
Let's take your liver tumor example on a CT scan. The intestines, the bones, they're in the image. But for finding a liver tumor, they're mostly noise. The model has to learn to focus on the liver tissue.
Right, filter out the distractions.
Exactly. This filtering lets the network create what we call representations or internal summaries of the input data,
Hmm.
highlighting the features most relevant for the task.
Representations, like a condensed version.
Kind of. And these representations are often expressed as an embedding. An embedding is basically the crucial information converted into a series of numbers, usually a vector, like a list of numbers, or
Oh.
maybe a matrix for something like an image.
A numerical code almost?
Yeah, you can think of it like that. These numbers might look meaningless to us, but they capture the essence of that data element that the model needs for its task. So for that brain MRI tumor detection, the model transforms the complex image data into a simplified embedding that really emphasizes the features indicating a tumor's presence and location.
Hmm.
This embedding is a much more manageable, highly informative version of the original input for the model to work with efficiently.
Okay, so the complex image gets distilled into a focused set of numbers. How do different types of neural networks handle creating and using these embeddings?
Different architectures have different strategies. Some are simpler, some use specialized subnetworks. A good example is the UNet architecture, which is really common in medical image segmentation and generation. Yeah, it uses two connected parts, an encoder and a decoder. The encoder takes the input scan and transforms it into that compressed embedding, isolating the relevant features.
Okay.
Then, the decoder takes that embedding and uses it to reconstruct a new image or a segmentation map, highlighting the areas of interest, like the tumor.
Ah, so it summarizes, then rebuilds with emphasis.
Precisely. The encoder is like a skilled summarizer, boiling down a long document, the scan, into key points,
Yeah.
the embedding. The decoder then uses those points to create a new, focused output, the segmented image.
That makes a lot of sense.
Yeah.
You also mentioned embeddings for language processing with transformer networks. How does that work?
Right. In language, transformers use embeddings to represent words in a way that captures not just their literal meaning, but also their relationships to other words.
Hmm.
Nuance.
Okay.
These models train on massive amounts of text-think libraries, the internet, to learn how words associate based on context.
Hmm.
So each word or phrase gets an embedding that list of numbers reflecting its characteristics. For example, the embeddings for car and motorcycle would be relatively similar because they often appear in contexts about transportation.
Makes sense.
But the embedding for ice cream would be very different, appearing in food context. Mathematically, you can imagine these embeddings as points in a high-dimensional space. Car and motorcycle would be close together, far from ice cream.
Okay, grouping similar concepts.
Exactly. And what's really amazing is they can capture abstract relationships, too. Like, the mathematical relationship between the embeddings for man and woman is often very similar to the relationship between king and queen. It reflects that underlying semantic concept.
Wow. That's pretty sophisticated. It's like it understands the underlying concepts. Okay, so we've got neural networks, embeddings. Now let's dive into specific architectures. You mentioned convolutional neural networks, CNNs, and transformer networks. What are the key differences? What are their strengths?
Right. So when designing a network, there are many ways to connect the neurons in layers. Over time, researchers found certain patterns or architectures work particularly well for specific data types and tasks.
Hmm.
Two hugely influential ones are CNNs and transformers. As we hinted, CNNs are fundamentally designed to analyze localized patterns using an operation called convolution. Transformers use a mechanism called self-attention to understand how every part of the data relates to every other part.
Local patterns versus the whole context. Got it.
Yeah.
Let's start with CMNs. Why are they so good for images, especially medical ones?
CNNs became incredibly popular for medical images because they're great at capturing spatial hierarchies and local patterns. Think textures, edges, simple shapes building up to complex ones.
Okay.
Each layer looks for specific visual features. Early layers find simple edges. Later layers combine those to find more complex structures relevant to the task.
Building blocks of vision.
Exactly. They process images using a grid-like structure, making them really good at detecting subtle changes in texture or intensity. That's invaluable in radiology dermatology, where fine details matter clinically.
Right.
The convolutional operations apply small filters across local parts of the image. This focus on local regions makes CNNs computationally efficient for images compared to some other methods like transformers, as they don't need to process the entire image at once in each layer.
So great for details and spatial relationships in images. What about transformers? You said they revolutionize language processing. How?
Transformers really change the game for tasks needing deep context and sequence understanding, especially language. Their key innovation is that self-attention mechanism.
Health attention.
Yeah, it lets the model weigh the importance of each part of the input data relative to every other part. It learns how much attention to pay to different words in a sentence, understanding word order and relationships, even between words far apart.
Okay, seeing the connections across the whole sequence.
Exactly. This is brilliant for identifying long-range dependencies and nuances in data. That's why transformers outperform CNNs in tasks needing that deep contextual understanding, text generation, translation, and increasingly processing medical documents. They grasp the overall meaning by looking at everything together.
Okay, CNNs for local image details, transformers for context and long-range links, especially in language. Are they strictly limited to those domains? Can they cross over?
Interestingly, yes, they can cross over. CNNs have shown some promise in processing sequential data, like time series medical data, though they aren't usually as good as transformers at capturing very long-term dependencies.
Okay.
And conversely, transformers, initially for language, can also process images quite effectively. They tend to focus more on overall geometrical patterns and long-range relationships within the image.
Interesting.
The fact that each has distinct strengths and can be adapted gives researchers a lot of flexibility. You pick the best tool for your specific data and task. Right. Choose the right architecture for the job.
Yeah.
Okay, let's move to the generative models themselves. You mentioned the field moves fast, older models are being overtaken. What are the dominant families of generative AI models we're seeing now?
Yeah, the landscape is changing incredibly quickly. Older models like Jan's generative adversarial networks and LSTMs, a type of recurrent neural network, were foundational. But today, the field is largely dominated by three main families: diffusion models, large language models, LLMs, and large multimodal models, LMMs.
Okay.
These three generally offer better performance and efficiency across a wide range of tasks compared to the older ones.
Let's start with the fusion models. What are they best known for?
Diffusion models are primarily famous for creating incredibly realistic visual data complex images, high fidelity videos. There's some research into using them for text, but their real strength right now is top quality visual output.
Hmm.
The underlying architecture often uses that UNet structure we talked about with its encoder-decoder, which is great for capturing and reconstructing fine special details. And how do they actually generate these visuals? The process sounds a bit weird, generating from noise.
Does sound counterintuitive. The core idea is learning to generate images, starting from random noise. During training, they're fed millions of real images, but these images are progressively degraded by adding noise, step by step, until they're just random static.
Yeah.
The model then learns to reverse this process. It learns how to take that random noise and gradually transform it back into a meaningful, coherent image. This learned denoising ability is what lets them generate totally new visuals from scratch,
Wow.
synthesizing images that look authentic and varied. So a model trained on nature photos could create entirely new, realistic landscapes it never saw in training.
So it's like learning to meticulously unblur an image until a clear picture emerges from pure randomness.
That's a really good way to think about it. Yeah. Now, they can operate in two modes: unconditioned and conditioned. Unconditioned models just generate based on learned patterns. Conditioned models take extra input to guide the output. For example, you could condition a model trained on seasonal images with a text prompt, like winter landscape or summer beach, and it generates something consistent.
Ah, so you can steer it.
Exactly.
Yeah.
Text prompts are common, like with Stable Diffusion. You describe the image style and content, it generates it. They can also do image-to-image transformations, like converting one MRI sequence type to another based on conditioning.
Mm-hmm.
They need significant computing power, but maybe slightly less data than transformer models, partly due to that convolutional UNet foundation.
Okay, diffusion models for amazing visuals. What about large language models, LLMs? We hear about them constantly. ChatGPT, Gemini, Claude.
Right. LLMs are the current champs for understanding and generating human-like text. They're trained on truly enormous data sets, vast amounts of text from the internet, books, articles. Their core mechanism is predicting the next word, or token, in a sequence, based on the preceding context. Next, token prediction. That's how they generate coherent text. A token is usually a word or a meaningful part of a word.
So they're basically incredibly sophisticated sentence completers, but on a massive scale.
Pretty much. And they achieve this using those transformer architectures we discussed, which excel at capturing long-range dependencies and language nuances. Transformers let them consider every part of the text in relation to what came before.
Right, that context again.
Exactly. Because of the huge data and complex architecture, training LLMs requires vast data sets and immense computational power. Very resource intensive.
Hmm.
But once trained, these foundation models can be adapted using post-training techniques for specific tasks like question answering, summarizing notes, generating explanations, lots of direct medical applications there.
Okay, LLMs master text. Now, large multimodal models, LMMs, the name suggests they handle more than just text.
That's right. LMMs are a big step beyond LLMs. While LMMs focus on language, LMMs are designed to interpret and process diverse data types, text, images, audio.
Okay, multiple modes.
Yeah, their output is often still text, but they can take in multiple input types to analyze and summarize complex information. For instance, an LMN could look at a chest X-ray and read the radiology report text, then generate a summary integrating findings from both.
So it can see the image and read the text, then synthesize.
That's the idea. The training is similar to LLM's large, diverse data sets, transformer architecture learning relationships across different data types.
Makes sense.
But as you can imagine, collecting and curating the training data for LMMs is even more complex and resource-intensive than for text-only LLMs.
Right, dealing with images and audio adds complexity.
Definitely. And it's worth noting, the lines between LLMs, LMMs, and diffusion models are getting blurrier. Some LMMs incorporate diffusion for visual generation. Text-to-image diffusion models often use transformers to understand the text prompts.
Oh.
You might also hear the term vision language model, or VLM. That usually means models handling just text and images, a subset of the broader LMM category, which might include audio too.
Got it. It's a very interconnected and fast-moving field. Okay, we've covered the core concepts and main model types. Let's shift focus now.
Hmm.
How do these models go from development labs to actually being used in places like hospitals? It's not just like installing software, right?
Absolutely not. Understanding that whole pipeline from development to deployment is crucial if you want to assess how practical these models are for medicine. Deployment brings in huge considerations: accessibility, privacy, a big one in healthcare customization. And a really key decision healthcare institutions face is whether to use proprietary AI models or open-weight ones. That choice impacts data control, ethics, costs, resources. It's pivotal.
Okay, let's break down the development process first. What are the main phases a model goes through?
Generally, most modern generative AI models go through three main phases: pre-training, the main training phase, and then post-training.
Pre-training, laying the groundwork. What happens there?
Pre-training is all about gathering and preparing the massive amounts of data needed to give the model a broad understanding of its domain.
Mm,
For LLMs, LMMs, this often means public internet data, but carefully filtered for quality and relevance.
right.
So for a medical LLM, you'd identify reputable sources, try to filter out non-medical stuff, and crucially, you have to deal with copyright and ethics only using licensed or permitted data.
Okay, data sourcing and cleaning.
Yeah. And then there's cleaning and standardizing,
Hmm.
removing duplicates, breaking text into those tokens we mentioned so the model can process it. This data prep, especially the human review parts, is incredibly resource intensive.
I bet.
That's why AI companies have teams of data engineers, and sometimes even use other pre-trained LLMs to help speed up parts of this data cleaning.
Wow, using AI to build AI. Okay, so that's the data prep. What about the core training phase?
That's where the heavy lifting happens. It's extremely compute intensive, needs specialized hardware, huge clusters of those GPUs. The model trains iteratively, sometimes for weeks or months. Engineers monitor constantly for errors,
Okay.
and it uses a ton of time and electricity. There are real environmental costs. Training one huge model can use as much energy as a small city, potentially.
That's staggering.
Yeah. The result of this phase is often called a foundation model, a general model trained on a huge corpus, ready to be adapted for specific applications.
Okay, pre-training gets the data. Core training builds the foundation model with lots of power. What's post-training for?
Post-training is about refining that foundation model for specific uses and aligning it with ethical and social expectations.
Ah, polishing it up.
Kind of. One technique is instruction tuning. This is less intense training, focused on changing the model's style, maybe making it answer questions instead of just completing sentences, rather than teaching it new facts.
Right.
Another big part is alignment, trying to make sure the model avoids biased, unethical, or harmful responses before it's released publicly.
Right, safety checks.
Exactly. Techniques like reinforcement learning with human feedback, or RLHF, are used here. Humans rate the model's outputs, and that feedback guides the model towards generating more desirable content and style.
Like teaching it manners and directing its skills. Okay, that's development. Now, deployment. How do people actually use these models in healthcare?
Right, so development is restricted, but deployment makes them accessible. Understanding the options is key for you. One way is out-of-the-box use.
Just using it as is.
Exactly. Using a pre-trained foundation model without modification, often accessed via cloud platforms, so you don't need the heavy hardware in-house.
Convenient.
Yeah. Users interact via prompts, get tailored outputs. This is where prompt engineering comes in, learning to ask questions effectively to get what you want. But the big assumption is the model already knows what you need it to know, which isn't always true, especially in specialized fields like medicine.
Right, the knowledge limitation we mentioned. So
Yeah.
what are the alternatives if out of the box isn't enough?
The main alternative is fine-tuning. This is that middle ground. You take a pre-trained foundation model and train a subset of its parameters on a targeted data set specific to your application.
Okay, specializing it.
Exactly. Like fine-tuning a general language model on radiology reports to make it better at summarizing findings or generating structured impressions for radiologists.
Got it.
It still needs extra compute resources and a curated data set, but less intense than the initial training. This is mostly done on open-weight models, where you have access to the model's weights.
Open weight, like
Yeah.
open source.
Similar concept, yeah.
Mhm.
But there are costs, data collection, processing, computation, and risks too. Like
Yeah.
catastrophic forgetting the model might get worse at things it used to know. Or it might just mimic the style of the fine-tuning data without really learning new substance.
Potential pitfalls. Okay, you mentioned the choice between proprietary and open weight models. This sounds crucial for healthcare. What's the difference?
It's a huge distinction impacting data control, cost, customization, everything in healthcare applications. Proprietary models are usually from commercial companies. You don't get access to the model weights or architecture.
Okay, it's a black box.
Pretty much. Access is usually via subscription cloud services. Think OpenAI's ChatGPT, Google's Gemini. The provider handles updates, security, maybe offers fine-tuning options.
Pros and cons?
Pros, often state-of-the-art performance, easier to get started. Cons, major data privacy concerns. Sending sensitive patient info to an external service could violate HIPAA, limiting use with protected health information.
Big issue for hospitals.
Huge. Some providers offer containerized deployment behind your firewall, but those contracts can be complex and resource-intensive to manage. On the plus side, it lifts the burden of model development and operation off the institution. Fees might be lower short-term if usage is sporadic.
Okay, so proprietary. Easy access, maybe lower initial cost, but serious data security hurdles.
Yeah.
What about open weight models?
Open-weight models, like Stable Diffusion for images, Meta's Llama, Microsoft's Olava, give you complete access to the model weights.
Full control.
Yes. This means you can run them entirely within your own secure network. Total control over data. That's a massive plus for healthcare compliance and privacy. Much more appealing for sensitive patient data.
Okay.
And they're more customizable because you have the weights. Examples include Stable Diffusion, Llama, Olava.
Downsides.
Cons. Requires substantial hardware investment, especially for fine-tuning. Cloud GPUs can get expensive long-term. You need more in-house technical expertise for maintenance, updates, troubleshooting, and performance might be slightly behind the very latest proprietary models, though that gap is closing. Importantly, there's no clear evidence yet that either approach consistently leads to better operations or clinical outcomes when you factor in all the costs and complexities.
So a major trade-off. Proprietary balances accessibility and power with data security risks. Open weight offers control and compliance vital for privacy, but needs bigger upfront investment and expertise. Critical factors for healthcare organizations.
Absolutely critical.
Okay, now we understand development and deployment. Let's get to the applications. What are people actually doing with generative AI in medicine today?
Right, the applications are really extensive and growing fast, especially in medical imaging. We can kind of group them into general applications where a model directly makes synthetic output and special applications, which rely on generative models within more complex setups.
Okay, let's start with the general applications. How is generative AI being used directly to create new data?
A big one is image generation and enhancement. Diffusion models, especially, can help overcome small or biased data sets by generating realistic synthetic images to augment training data for other AI models.
Making more data to train with.
Exactly. For example, a model called CXR-IRGen generates synthetic but realistic chest X-rays from human chroms. Another, multitask brain tumor inpainting, can digitally add or remove tumors from brain MRIs, great for creating diverse training scenarios.
Wow.
It can even help address data set bias, transforming one radiograph to look like it's from a patient of a different race, for example, while keeping the original medical features intact.
That's powerful.
And beyond training data, there are clinical uses.
Mm-mm.
Super-resolution models, often diffusion-based, can produce higher-resolution versions of various images, CT, MRI, ultrasound, pathology slides. Useful if equipment is limited or to speed up studies.
Mm-hmm.
Image-to-image conversion like CT to synthetic MRI, even generating 3D rotations of radiographs from a single 2D image, letting clinicians visualize from multiple angles without more radiation.
Okay.
And interestingly, these generation models can sometimes be adapted for discriminative tasks too, like segmentation or anomaly detection.
So a huge range in imaging, improving data, enhancing images, even changing modalities. What about text? LLMs are the text experts, right? How are they being applied medically?
LLMs are definitely transforming medical text. We're seeing systems emerge that use LLMs to automatically generate clinical notes from patient-provider conversations.
Dictation on steroids?
Kind of, yeah.
Mm-hmm.
Potentially improving accuracy and efficiency, freeing up clinician time. There are also specialized models like HEAL or Mistral 7B, getting good at generating detailed notes for specific things, like discharge summaries for better handoffs.
Okay.
Another big area is automated radiology report generation. LLMs analyze findings from images, structure reports, highlight critical stuff, even provide interpretations.
Mm-hmm.
The hope is to reduce cognitive load, minimize errors, standardize documentation. But importantly, some early evidence also suggests LLMs might sometimes increase workload, or that AI clinician collaboration isn't always better than either alone. So we need careful evaluation.
Yeah, nuance is key. You need to ensure it actually helps. What other text applications?
Patient communication is another big one. Yeah. LLMs can translate complex medical info into easily understandable language.
Making jargon accessible.
Exactly. Better understanding, engagement, autonomy, stronger patient-provider relationships. And then there's medical education.
How so?
LLMs can create personalized study resources, generate realistic exam-style questions with explanations tied to clinical scenarios, helping students practice critical thinking. They can even act as virtual tutors for complex topics.
So impacting clinicians, patients, and trainees. You also mentioned audio and video generation. Less common, you said, but what's the potential there?
Yeah, less explored, but still significant value, especially for training, communication, education. It enables new ways to enhance these areas,
Mhm.
generating realistic surgical videos, clinical sounds like heart murmurs, or transcriptions of spoken notes to expand data sets for other AI models, improving multimodal tasks.
Okay.
High-fidelity synthetic surgical videos or sound simulations can expose trainees to rare scenarios safely, enriching education to interactive patient avatars for practicing difficult conversations in diverse contexts. Yeah. Think breaking bad news or handling cultural sensitivities.
That could be really valuable practice.
Yeah. Potential for live translation in healthcare too, breaking language barriers, hopefully leading to more empathetic interactions. Video generation could enhance pre-op planning or offer real-time guidance during procedures. And patient education generating accessible explanation videos from text about procedures.
Really innovative uses of synthetic media. Okay, let's move to those special applications. How are they different?
They might not directly generate synthetic data as their main output. Instead, they often rely heavily on generative models within more complex AI systems or involve configurations of multiple AI models working together.
Got it. Can you give some examples in medicine?
Sure, a big category is diagnostic, prognostic, and treatment planning aids. Diagnosis itself is mostly discriminative, but generative AI models, especially LMMs, can be valuable backbones in complex pipelines for patient assessment. They leverage generative AI, especially LMMs, to integrate diverse data imaging, text, records for richer, context-aware decision support.
Okay.
For instance, research shows instruction-tuned LMMs improving ECG interpretation accuracy, identifying heart abnormalities even with limited data. Other LMMs offer detailed CT interpretations for orthopedic diagnosis, providing real-time support.
Mm-hmm.
There's a model called Report Guided Net that integrates radiology report text with brain MRI data to boost lesion detection accuracy and interpretability. It even provides visual aids showing where it found things, better than other models sometimes.
Integrating text and image context. Clever.
Yeah. And models like Ethos Transformer are predicting patient trajectories using zero-shot learning, simulating treatment paths from health data to help plan personalized care.
So, using generative capabilities to synthesize complex patient info for better decisions. What about retrieval-augmented generation, Hera? You flagged that as important?
RAG is really important in healthcare because it tackles key LLM limitations:
Yeah.
accuracy, up-to-date knowledge, and handling huge amounts of info beyond their context window.
Context window. The amount of info they can handle at once.
Exactly. If the input needed exceeds that window, LLMs truncate or compress, leading to simplistic or wrong answers. Even large context windows can struggle with too much data.
Okay.
Plus, LLMs rely on static training data. They don't know about new guidelines or research published after they were trained. This leads to that risk of hallucinations, plausible but wrong or outdated info. Knowledge cutoff is a real problem in evolving healthcare.
Right. So how does GRAG help?
RGAG lets LLMs dynamically access relevant external information as needed. It's like giving the LLM a library card and telling it to look things up before answering.
Okay, how does that work technically, roughly?
It encodes documents, guidelines, papers, databases, and the user's query into embeddings capturing semantic meaning. Then it retrieves the most relevant documents from that external knowledge base.
Finds the right pages in the library.
Precisely. It then provides those retrieved documents to the LLM as context, along with the original query. The LMM uses fresh, relevant context to generate a more accurate, up-to-date, and grounded response.
Ah, grounding the answer in external facts.
Exactly. It's a huge step forward for overcoming LLM limits, where accuracy and timeliness are critical. We're seeing RGI systems like Almanac for clinical medicine, retrieving from curated sources for guideline-compliant recommendations. Self-BioRag improves generating accurate biomedical explanations. Custom ChatGPT models using RGI for guideline-compliant advice in specialties like nephrology.
Sounds incredibly useful for keeping AI advice current and reliable in medicine. Okay, the last special application, multi-agent setups. What's that about?
Multi-agent setups involve multiple agents, AI models, or modules working together on a common goal. Each agent has a specialized role.
Like a team of AIs.
Exactly. It distributes the cognitive load, handles complex workflows more dynamically and efficiently. It's a newer trend in healthcare AI, but showing real potential.
Can you give a medical example?
Imagine a system for managing sepsis. You might have one agent monitoring vital signs, another analyzing lab results for infection markers, another checking treatment guidelines for recommendations.
Okay.
They communicate. If vitals drop, that agent alerts the others. The lab agent prioritizes sepsis markers. The treatment agent preps intervention options. This coordination could speed up response times, potentially improving outcomes in time-sensitive cases like sepsis.
Makes sense. A coordinated response.
Yeah. There are frameworks like Clinical Agent being developed for clinical trials, streamlining eligibility screening, data analysis, also valuable in education and research.
How so?
Projects like Medico use agents playing roles, expert physician, radiologist, virtual patient, to simulate realistic scenarios for interactive learning. AI Hospital simulates patient-provider interactions to assess diagnostic approaches, refine conclusions, mitigate biases in research.
Fascinating. Like having a specialized AI team collaborate. Okay, we've covered a lot of concepts, models, applications, both general and special, but we absolutely have to talk about the limitations. What are the key hurdles?
You're absolutely right. It's crucial to acknowledge the limitations for responsible integration. We could look at about 5 key challenges and the mitigation strategies being explored.
Okay, let's start with limitation 1, gaps in knowledge.
Right. As we've said, LMMs relying on static training data. Their knowledge is frozen at the time of training. They don't know recent medical advances, updated guidelines, new treatments. That's a clinical risk outdated guidance. Also, the training data, while huge, isn't comprehensive. Many specialized resources, rare disease info, cutting-edge research might be missing.
So they might just not know about niche or very new topics.
Exactly. They might give speculative or incomplete answers.
How do we mitigate this knowledge gap?
Well, RAE is a primary strategy integrating real-time data queries.
Right, the library card.
Yeah. Also enabling real-time internet search capabilities. Some LLMs and tools like Perplexity are doing this now. And fine-tuning models on recent curated datasets is an option, but remembering the drawbacks of fine-tuning we discussed.
Okay, so RA and search help, fine-tuning is trickier. Limitation 2, uncertainties and hallucinations.
This is a big one. The tendency for these models to produce hallucinations, confident-sounding, yet incorrect or fabricated responses.
Why do they do that?
It stems from how they work generating plausible language patterns, not necessarily verified information. They mimic human language well, so wrong info can seem credible,
Mm-hmm.
and they rarely admit uncertainty. They prefer confident answers even with insufficient info. That's especially concerning in medicine, where authoritative-sounding wrong outputs can mislead.
Absolutely critical. How do we mitigate hallucinations?
Again, RA helps by grounding responses in verified data, but it doesn't guarantee correctness.
Right.
A key area is incorporating methods for models to estimate and communicate their uncertainty. Developing models with uncertainty quantification capabilities, assigning confidence levels to outputs. Healthcare users should really push for this.
So getting the AI to say, I'm not sure about this part.
Yeah. Essentially, yes, or providing a probability or confidence score. Limitation 3, bias and fairness. This is a known issue in AI generally, right?
Yeah, we hear a lot about AI bias.
It's significant. Generative AI can inherit and amplify biases from training data, model design, evaluation methods. Biased AI can produce skewed outputs, perpetuating healthcare disparities.
How does the bias get in?
Training data is a big source. If data comes mainly from the internet or specific institutions, demographic or cultural biases in that data influence the model. A model trained in one region might be less relevant or misleading elsewhere, risking health inequities.
So how do we fight bias?
It requires effort on multiple fronts. Using inclusive training data sets representing diverse populations, conditions, treatments, generating synthetic data to address underrepresentation,
Mhm.
creating and applying diverse benchmarks for evaluation. But we need caution interpreting performance on public benchmarks. Potential data leakage can inflate scores.
Okay, better data, better testing, ongoing vigilance. Limitation 4, modern interpretability, the black box problem.
It's exactly. Generative AI models, especially neural networks, are often black boxes. Complex structures make it hard to trace why they produce a certain output.
And that's a problem in healthcare.
Huge problem. Clinicians need to understand the reasoning for trust and accountability. They need assurance the AI's reasoning is medically sound. Current models often lack mechanisms to explain themselves in human understandable terms.
So we don't know how it reached the conclusion. How can we improve interpretability?
It's a major research area. For image-based discriminative models, visualization tools like heat maps can show where the model is looking. But even these have limitations and biases.
Okay.
Understanding text generative models is even harder. Some research proposes methods to uncover internal concepts, but comprehensive interpretation is still a long way off.
So making the black box more transparent is a major ongoing challenge. Okay, final limitation. Regulatory and ethical issues.
Yes, rapid integration brings complex challenges. The black box nature makes assessing reliability difficult, especially for autonomous inferences without clear reasoning.
Accountability issues.
Definitely. Opacity limits verifying accuracy, raises accountability concerns if things go wrong. Ethical issues like bias, perpetuating inequities are significant. And the evolving nature requires ongoing monitoring for efficacy and safety, which is hard to standardize.
How are regulators like the FDA handling this?
They're evolving frameworks, often using a risk-based approach for AI medical devices.
Yeah.
The FDA uses a total product lifecycle approach, monitoring from pre-market through post-market surveillance, evaluating real-world performance continuously.
Mm-hmm.
But it's challenging for them. Rapid learning, updates, unintended effects require new approaches for long-term monitoring, accountability, risk mitigation. Regulatory resources also need to evolve to keep pace.
A complex dance between innovation and safety oversight. Okay, well, we have certainly covered a huge amount of ground today. A real deep dive into generative AI and medicine concepts, models, applications, and those critical limitations.
Yes, the aim was really to give you that solid foundation.
Yeah.
Explaining how these models differ, their uses in imaging, documentation, education, decision support, but also hitting hard on the challenges, knowledge gaps, hallucinations, interpretability, bias, regulation.
And as we've seen, integrating this technology requires a really thoughtful, data-driven approach, balancing the huge potential with the real limitations. That needs regulatory oversight, technical improvements, and transparency in how AI decisions are made.
Absolutely.
Right.
And while a lot falls to tech stakeholders and leadership, individual practitioners like you also have a responsibility as you encounter this new tech. You need to be informed, ask critical questions.
So as you, our listener, reflect on all this, the potential, the hurdles, here's a final thought. Considering your specific field in medicine, what single aspect of implementing generative AI do you believe warrants the most immediate focused attention right now? And why is that aspect so critical at this moment? Something to definitely mull over as this field continues its breakneck evolution.